Okay, so here's a rate of change function. One over 1 plus x squared. I want you to represent the accumulation function. It starts at x equals -1. I want you to represent that in open form and represent it in closed form. So review from Wednesday. Can you do it? What's that? That's the rate. That's the rate of change. So we can represent accumulation. This is rate of change. Rate of change here. So what will the structure of the open form accumulation function be? It's the general structure. An integral, right? An integral. In graphing calculator, that's Control-Shift-I. Okay, what's my lower limit of integration? Upper limit. Good. What function? I could retype 1 over 1 plus t squared, or do just, I've already defined r up here, so I can just use it. And then I want dt. There's the open form. So if I want to write this in closed form, that means I need what kind of function relative to r of x? Okay, they're both accumulation functions. But what kind of function do I need relative to r? Rate of change of r? Antiderivative, right? This is the derivative of the function that I need. That's the way you got to think about it. If this is rate of change and I'm trying to do a closed form accumulation, then this is the derivative of some function that I need to write a closed form accumulation function. What function has this as its derivative? Do you remember from the mastery test? Arctangent. Okay? So if I want to write this in closed form, I'm going to write arctangent of x. So I want the accumulation from 1 to x. So if I have a closed form, I can just write, is that right? Am I done? Minus arctan of 1. So when I turn on these graphs, what should happen? Should be the same graph, right? So whether it's open form or closed form, I should have the same accumulation function. So just for suspense sake, I'll do the open form first. Okay? And when I turn on the closed form, this is how you can use graphing calculator to check a closed form accumulation function against the trusted form. The trusted form is the open form. We know that's right. So we can check to see if this is right. So I turn it on in black, and it should be right on top of it. So yeah, so the inverse trig functions in GC are a cos, a sine, a tan. That's how you get the arctan, the inverse trig functions. Okay, so where are we starting accumulating from? 1? Is that right? And because that we see if we plugged 1 into this function, we ought to have 0 accumulation, right? Okay, so then why is there all this graph showing out to the left? If we're starting accumulating at 1, then what's with all this graph back here? So, because I can look at this. I'm going up out to the left here. It just keeps going and going and going. So, is that part of the accumulation function or not? Some are saying yes, some are saying no. So we have to, so obviously it's coming from this rate, it's coming from our, it's part of the graph of our, what we've graphed here of our accumulation function. It's coming from this rate of change. For rate of change less than -1, we get a corresponding accumulation even though we're thinking about starting at 1. So we had to kind of revise the way we're thinking about this a little bit. Okay, because we have accumulation out there to the left of 1. To this point, we're saying, okay, we're going to start accumulating at 1. But a picture tells 1,000 words. There was already accumulation before 1. Okay, so here's a way to think about this. So you know, like on a scale, you can stand on the scale, put something on the scale, and then there's like a reset button, right? And what happens when you hit the reset button? When you're standing on, or you have something on the scale? It's like it reads 0. Are you all familiar with this? So let's go back to our sand example and think about our sand example in these terms, okay? No, that's not it. So remember, so if we have a rate of change function, R, this accumulation function defined by R is capital F, A to X, RT dt. So far we've said A is the starting point of accumulation. Okay? And F is some antiderivative of R. Okay? But remember our sand example. So suppose at C seconds, just anywhere along here, the sand is dumping onto the scale. Somewhere here at C seconds. We hit the reset button on the scale. So if this is A, say in this case A is 0, okay? So this represents the total amount of sand, the weight of all the sand on the scale. If we hit reset at C, how can we rewrite that total weight of sand on the scale? Yeah, so what we can do is the total weight of sand on the scale of X seconds we can write as in 2 parts. We can write it as the weight accumulated in the first C seconds. So that would be from 0 to C, integral from A to C. Plus the sand that integrates after we reset. And that turns out to be the scale reading, right? So that the integral from C to X, that would be after the reset. That value would be the scale reading. So how can we rewrite that part? So the scale reading then, if we rewrite this equation, would be this, the total weight of sand on the scale minus the weight before the reset. The weight that, does that make sense? Should make sense, right? Okay, well, what is the total weight of sand on the scale? That's just f of x. And what's the total amount in the first C seconds? So the total amount of sand on the scale is this. The total amount in the first C seconds is f of c, right? So the scale reading, or the amount after the reset, the accumulated amount after the reset, is the total amount of weight on the scale, f of x, minus the amount of weight that poured on the scale before we reset, f of c. Does it make sense? So we want to think of this lower limit now. Do I have something else here? Okay, so what we want to do now is we want to think of this lower limit not so much as the starting point of accumulation. So we started accumulating before. C is like we're going to do a reset, and we're going to get 0 accumulation wherever we do that lower limit of accumulation. So you think of it as weight, you think of it as hitting a reset button on the scale, and now we're going to start from 0. But there was already accumulation before. Okay? So it's like the total amount of accumulation minus the accumulation up to our reset point is going to then give us how much accumulation we had since the reset. Doesn't make sense. So let's go back to the tangent example. Which was here. So how can we think of this differently? So this, instead of the function starting at x equals 1, the accumulation, we can think of the accumulation starting where? Where can we think of the accumulation starting? So the 1 is going to be our reset. So we represent the accumulation function with a reset at x equals 1. So we're going to force it at x equals 1 to kind of start over. It's going to reset x equals 1, so we get 0 accumulation at 1. Where did it start accumulating? Where? Negative infinity. So it had been accumulating since negative infinity, and then we chose a reset at 1, so we got 0 accumulation at 1. So we're altering this lower limit of integration. We're altering the way we're thinking about it. It's no longer where we start accumulating. We think about we're going to start accumulating at negative infinity. Now that lower limit of integration, in this case 1, is this reset where we're going to force that accumulation function to start over and give us 0 there. Okay? So let's try another example. So same type of example, but now I want to represent the accumulation function with a reset at x equals negative 2.5. Where do we start accumulating? Far, 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 far to the left. A huge negative number. And then it's going to accumulate, but then we're going to force it to reset at negative 2.5. Go. Okay, so the rate function, do we think of it as a derivative or an antiderivative? You look at that. Is that a derivative or an antiderivative? We want to think of that as a derivative. As the rate of change function, it's a derivative, and our accumulation function will be the antiderivative, or the function whose derivative is that. And so here's where being a master is so important, because now we have to kind of ask ourselves, instead of following the rules to take a derivative, now we have to ask ourselves, what function, when we follow the rules, gives us that as a derivative? So I tried to give you a nice rigged one there. Lots of you got it. Sine of? So sine of x to the okay, so we have two ways to check this as the antiderivative now. So there's two ways. So what's one way that we can check to see if we've got this accumulation function or antiderivative correct? Sam, what do you say? Right, take the derivative. go ahead and take the derivative, and what should you get? You ought to get r. So that's the first way you can check it. What's another way we can check it? Am I going to graph this? What am I going to graph? Minus sine of negative 2.5 to the... Two ways I can check it. I can take the derivative of sine to the 4/3. I ought to get my rate function if it's right. Or I can just graph it against the open form. Open form is a trusted form. So we know that this is the right antiderivative accumulation function with a reset at negative 2.5. So how does that confirm that the reset is at negative 2.5? What do you look at? Right there. Is there a 0 at negative 2.5? Yes. So that's what we're looking at our reset. We get a 0 accumulation, and we start accumulating from there. But really, the accumulation really started at negative infinity. Okay? So we can check our closed form by turning it on, and we get nothing. What did we do wrong? Something. What's the order of operations? Exponent first, and then take the opposite. But we want negative 2.5 to the 4/3. So we can just highlight. Got to do it again. Ready? Here we go. Still didn't work. What happened? I'm stumped. We did something wrong though. What's wrong?
I think it's the 4/3 exponents.
Really?
Yeah.
No. Okay, we'll have to solve this mystery later. I don't know what's wrong. Anyway, anybody got another idea? Okay, well there is an explanation. It's just we got to figure out what it is. TAs, any ideas? Where are my TAs? Oh, they're hiding. Okay, I'll definitely figure this out and get back to you. But we have this is definitely the right open form. I don't see anything wrong with the closed form. I don't see anything wrong with it. Let's move onward. Okay, so remember we introduced what an improper integral is. Okay, so an improper integral, if you don't see any limits, that represents all antiderivatives of our fx. So we can think about all antiderivatives. They start accumulating, functions that start accumulating at negative infinity, and then you can choose any reset that you want. You choose any reset along the way, and that'll be your lower limit of integration. And so now when you see an A there, you don't think of like truly starting accumulating there, but resetting accumulation there. So this is our reset. Okay, it would go here. If we were writing it, if we were writing it explicitly with the limits, it's not a 0. Sorry, it's just a placeholder. So I'll just write an A. But if you don't see anything there, it just means generically that we're resetting anywhere we want. So it's every single accumulation function. Okay? And so then this is often written as f of x plus, this will be some constant. So that plus c is equal to the opposite of f of a. That's that vertical shift that we need to get a 0 at a. So that's how we're going to vertically shift the generic accumulation function so that at x equals a, the accumulation is 0. Okay, so Fundamental Theorem of Calculus. We've been doing it all semester, so there's really nothing left to say except to summarize it. And it says that an accumulation function represented in integral open form with a rate of change of f of x can be written as capital F of x minus f of a, where f is any antiderivative of f. So this is nothing new now. It's just we're putting a name on it. The Fundamental Theorem of Calculus. This brings together probably 75 or 80% of what we've been working on all semester. If you plug in x equals b for x, so if you evaluate this function at x equals b, you get the net change from a to b. So that looks like this. So that's just plugging in a value for where we're going to stop accumulating. So we're going to stop at a number b, and so the amount of accumulation, the net accumulation, is any antiderivative evaluated at b minus any antiderivative evaluated at a. So there's a different way to write this last part, an alternate notation. You just write the antiderivative, and then you put this vertical bar with an a on the bottom of it and a b on the top. And that what I've written in red, it means exactly the same thing as what's in the red box. These are two different ways to say the exact same thing. It means plug b in, plug a in, and subtract. Okay, so the real advantage is if we can get a closed form version of capital F. If we can get a closed form version of capital F, then we have an accumulation function that's a lot more ready to use and just give us lots of outputs of accumulation quickly. Okay, and so that's kind of what we're working on next. But let's check this out here. So checking this property, I have two rate functions. Okay, we're going to go ahead and find in GC, we'll just get a value for, in open form, the accumulation from 2 to 5 at that rate. And then we want to use our knowledge and mastery test to come up with a closed form antiderivative for each of these. Practice using the alternate form for representing f of 5 minus f of 2, and then compute the value of f of 5, f of 2, and compare it to the first column to make sure that they're the same. Okay? So let's get graphing calculator here. So why don't you, while I'm getting this set up, why don't you work on these two? So this is kind of the algebra. Thinking of this as the derivative of some function from the mastery test. What function's derivative would be this? And what function's derivative would be this? So these are writing out the closed form antiderivative. You do that while I set this up. Hold on, coming back. Okay, anybody got it? First one? In closed form. What is that in closed form? Square root of? Did you figure that out? And if you're not sure, what can you do? How can you check that? What's one way you can check that? Take the derivative and you should get the r function. Take the derivative of that, you should get the r function. Okay, so what's an alternate form for writing f5 minus f2? So it's that, and then you write the bar like this, and then you write 2, and you write 5. That is the same, that's equal to this. Because our capital F function is right here. Okay, so let's compute that. So you see that the open form gave a value of 1.4235. So now I'm going to do what? I'm going to do option 3 times 5 minus what? 3 times Okay, is this the only antiderivative of this rate function? Give me another one. How can I get a different one that's valid?
Add any constant.
Add anything. So make it good. Add what?
16.2.
16.2. So I'm going to come up here and I'm going to add 16.2. I should have defined it as f of x radical. All right, so instead I'm going to do, here I'm going to do f of 5 minus f of 2, right? And there it is. Okay, so if I come here and I add 16.2 to this fx, how is it going to change f of 5 minus f of 2? Not like that. Hey, notice, it didn't budge, right? Why? Because that capital F can be any antiderivative. Any antiderivative of r, and it will give us the right net change. So I can make it 100,000. The net change is still 1.4235. That's what the fundamental theorem says. This capital F function can be any antiderivative of r. Then the net change is the same. It doesn't matter how high up or down the accumulation function is or where it resets. If you have an amount of change between two x values, will be the same. Okay, what'd you get for this closed form here? E to the negative x. How do we get a derivative of x? X squared? Does that do it? No, we need a 1/2 with that too, right? What about the derivative of, Jose is saying, what about the derivative of e to the minus x? Is that e to the minus x? No, by chain rule you'd get another negative. So we need to include a negative there. All right, let me just do this. Okay, 10.629. What did we put for this here? Negative e to the negative x. Negative e to the negative x plus 0.5 x squared. Plus any constant. Any antiderivative will give that same net change. So we can add any constant that you want. You get the same net change, open form or closed form. Okay, exams Wednesday night. You got the review outline and lots of quizzes to work on. Be ready. It's hard.